Performance enhancement of permanent magnet DC motor with SEPIC converter through higher order sliding surface. ID number 8811. The authors are R. Dhanashekhar, S. Ganesh Kumar and Marco Rivera. Abstract. The primary concern of this article is to stabilize the rotating speed of a permanent magnet DC motor driven by a SEPIC converter under various loaded conditions. In this article, the authors proposed a new higher order proportional integral derivative sliding surface, that is PIDSS, and compared with classical sliding surface, sliding mode control and a proportional integral controller, taking into consideration of peak overshoot, steady state error and settling time. Both simulation and experimental results are obtained satisfactorily. Contributions. A PIDSS with a second order time derivative is proposed and compared with a second order classical sliding surface. The restriction of the order of the sliding surface for implementation is realized by investigating via relative degree and order of the system. The behavior of the PIDSS controller is analyzed under varying reference signal and load torque conditions. The proposed higher order PIDSS controller improves the system performance by reducing steady state error, peak overshoot and settling time even under loaded conditions. Generalized procedure for designing higher order sliding mode control. Selection of sliding surface, then compute the derivatives of sliding surface, find the equivalent signal from the higher order derivatives, then find the switching signal through homogeneity approach. Acquire the final control law in the combination of continuous and discontinuous signal. If the desired region is attained, then the PWM generation is only by the continuous signal, or both continuous and discontinuous signal will play. Circuit description of SEPIC converter fed PMDC motor. The circuit consists of fourth order SEPIC converter combined with permanent magnet DC motor. So here the steady state equations are represented. Simulation analysis. Table 1 shows the SEPIC converter and PMDC motor parameters. Here the authors used 18 watt permanent magnet DC motor. Table 2 shows the details of machine operation. For various time period, the reference speed profile and load torque profile is shown. Simulation has done for constant load torque condition, frictional load torque, fan type load torque and propeller load torque conditions. So subdivision A, the performance under constant load torque conditions. For various speed profile and load torque profile, the speed responses has been shown here for classical sliding surface, PIDSS, proportional integral controller and a sliding mode controller. Simulation results for frictional torque conditions, fan torque conditions and propeller torque conditions as shown here. Table 4 represents the comparison of PIC, SMC, second order SMC with classical sliding surface and proportional integral derivative sliding surface. The table 4 represents the speed settling time in seconds, steady state error in percentage and peak overshoot in percentage for various time period. Experimental setup. Laboratory setup for SEPIC converter fed PMDC motor, which consists of PMDC machine, 6 volt DC supply, converter circuit, 100 MHz digital storage oscilloscope and FPGA controller. Here the results shown for speed, armature current and armature voltage evaluations for second order SMC with the classical sliding surface and proportional integral derivative sliding surface for various time period. Conclusion: the authors simulated for SEPIC converter with a PMDC motor for various load torques. The simulation results indicate the exemplary performance of PIDSS in comparison with CSS, SMC and PIC. The experimental setup is built for verifying the above under constant load torque conditions. The proposed method is effective in both the estimation and rejection of disturbances. Future scope: it is extended for various higher order converters and loader situations. Author's bibliography. Thank you.